Good morning, everyone. Now we are going to start our physics class. In today's session, we'll just discuss about the defects in crystal, that is chapter 2. We are dealing with the chapter 2. In the chapter 2, we had discussed about the crystal structure and their properties and X-ray diffraction and the different techniques of X-ray diffraction. In this particular chapter, we'll just discuss about the lattice defects. Now, what is actually this lattice defect is all about? Now, in the uh, we just go for the what you can say lattice defects. So defects are nothing but it is imaginary what you can say. We'll just start it with this starting introduction first of all. So you know that the crystal is having a regular uh, nature of regular arrangement of the atoms. So we say that regular periodic arrangement of the atoms, and if there is any variation or the deviation from the regular arrangement of the atoms, or we'll say in the physics language, periodicity. So any deviation from the periodicity is known as a defects or imperfection in the crystal. Now, what is actually the basic definition of crystal defect? So the variation from perfect arrangement of the atomic sites or atomic arrays in the given crystal is known as crystal defect. Right. So the crystal defects are definitely what is the need of studying the crystal defects. So the crystal defects actually uh, affect the influence the properties of the material or the crystals. Right. How this what type of properties we are talking about? So we are talking about mechanical properties, strength and ductility, and the structure, crystal structure, crystal growth, dielectric strength, and definitely very, very important conductivity and etc. So we know that in a perfect crystal, every atom will have its own position, and that particular position will be in a systematic manner. Right? It means that you think that every atom will be there in a sequential order. That is not the case. There is no perfect crystal, right? So that is ideal one, right? So practically you don't find that in the crystals the atoms are arranged in a regular fashion. So that is the reason that we need to understand the defects in the crystal. So therefore, definitely crystals have some impurities or defects. That defects in the crystal maybe it may be a very small, that is point like a line type of defect, surface or volume defect. So these defects are actually depend upon the dimensions also. So if you talk about the basic classification of the crystal defect, so we are having point defects, that is also known as zero dimensional defects, and line defects, that is one dimensional defects, and surface defects, that is two dimensional defects, and volume defects. So in the last class we just have gone for the this point, line defect, surface defect. I have explained you. So this is only the briefing of whatever uh, we have learned in the previous classes. So next, what is actually the meaning of point defects? Here we are going to learn. See, this is a theoretical concept here. So that theoretical concept I will show you in the end of this particular class. I will show you the video of engineering materials where you'll find that why we need to uh, understand the crystal structure or crystal properties and what are the defects, point defects, and different types of defects. Why there is a need of studying first of all the crystal structure, and why we are studying what the defects in the crystal. So that particular thing that we are going to understand, you are going to understand in a better way when we see the video, right? So at the end of this class, I will show you the video, and in that video, definitely, I think that you will get an exact idea that as an engineer, what is the importance of engineering material and where actually these engineering materials are being used in daily life, and how this engineering materials are very, very important part of our life. So definitely we will see that particular video, and I think that you will get a very clear idea regarding the engineering material and why actually you are studying this physics chapter 1 and chapter 2, that is unit 1 chapter 1 and chapter 2. And definitely when we go to the unit 2, I will show the other videos also. For each chapter I will show some video to understand it in a practical manner, so why there is a need of studying that particular chapter. So definitely, we'll in the later section, in the later session, we are going to see the video. We are going to see the video, and you'll definitely, what you can say, have a very better understanding regarding the things that you are going to learn in the chapter one and chapter two. So now we'll move on to our regular topic, that is point defects. So you know that point defects are one-dimensional defect. Just now we had a discussion about these point defects depending upon the dimensions. So point defects are one dimension defects. So what is the meaning of this point defect? So if the atom is missing uh, in a irregular place in the lattice structure, so we'll say that that particular defect is known as point defect. So point defect actually produces a very small strain in a small volume of the crystal which is surrounding the crystal, and but it doesn't affect the exact what you can say the perfection uh, of the parts of the crystal. So what does this mean? So you need to understand here that what is actually the meaning of point defect actually. So it is a missing what is an atom, right, in a very irregular place, right? So in the lattice structure, so therefore such irregular presence absence of the atom will call such defect is known as the point defect, right? So in general the point defects have been again subclassified as four types, right? Subclassification of point defects is actually it has been classified into vacancies, interstitial defects, substitutional defects, and electronic defects. So these are the major subclassification of point defects. So actually, in the later section, will I will give you the when I will give you the notes, you'll understand that what are the actual advantages of this point defect, studying point defects. So now for this instant, we just understand the what is actually the vacancies that comes under point defect. So what is vacancy? There's a very simple point defect in a crystal in which you'll find, see, there is a regular arrangement of atoms, and at the middle, at exactly, so this is the what you can say a vacant atomic site where the atom is missing. So we'll call such a missing atom uh, is known as the vacancies. The open space or the atomic vacant atomic site is known as vacancy. You can see exact definition is given as the defects that is due to the missing atoms or the atomic site at the lattice sites are called vacancies. So this is the basic definition. The defect which is due to the missing atoms at where it is missing, the atom is missing at the normal lattice site. So therefore, we'll call such a missing atom as the vacancies. So a crystal lattice with the vacancy defect is shown in the figure. You can see that there is a missing atom here. So I should say that the given point defect is nothing but it is a vacancy. Now we'll move to the next one. Vacancy defects are why it is due to what is the cause of it. So vacancy defects are due to the imperfect packing during the formation of the crystal. So as I already told you that we can grow the crystal in the lab also. So here, if there is a if there is any deviation in the what the closeness of the atom during the formation of the crystal, and how this packing or the closeness of atom, it is actually due to the thermal vibrations of the atom. When you increase the temperature at very high temperature, there will be some deviation in the arrangement of the atom, and what will happen is that there will be some missing of the atom from the lattice side. So that particular defect is known as a vacancy. So at high temperature, atoms are frequently and irregularly change their positions, leaving empty sites behind their positions. So we'll call that at a very high temperature. So this defect is completely temperature dependent, right? So that we can conclude from our talk that if the temperature is high, then we can say that definitely the atoms will not remain in the periodic manner. It will be some different variation. Find the variation, it will leave the normal site, and that vacant lattice site will call such defect as the vacancy defect. And what is that thermal energy? If you give some amount of temperature to it, definitely it will, we call that as thermal energy, and that thermal energy is of the order 1 electron volt. So per vacancy means what? Here, whichever the lattice site, whichever the atom is missing, so each atom will definitely will have a thermal energy of 1 electron volt, right? Through which so the number of vacancy per unit volume of the crystal, definitely I said in the in our last sentence that it depends upon the temperature. So and particularly here we talk about the vacancies. So it means again I'm repeating the same thing here. So vacancies are nothing but vacant lattice sites. Vacant lattice sites are vacant atomic sites in which is present in the crystal is known as vacancy. So particularly if you talk about the ionic crystals, see here we are again we are moving to the ionic crystal. So ionic crystal, right? So when I say the ionic crystal, so the ionic crystal, there are two types of point defects here. So what is that two types of point defects? That is called Schottky defects and Frenkel defect. That Schottky and the Frenkel defect, you already, I think that they are having very clear idea regarding the Schottky defect and the Frenkel defect in the intermediate. Okay, no problem if you don't have any, right? What you can we if you have forgotten, then we'll have a glance of it, shortcut effect definition. So what is actually the meaning of shortcut effect and Frenkel defect? So this is occurring in the particular ionic crystal. So now what is actually shortcut effect? Say shortcut effect come under the category of sub classification of point defect, that is the vacancy. So it is a very special case of vacancy defects in the ionic crystal. So what is the meaning of Schottky defect here? So when you talk about ions, ionic defect, ions. So what is mean when a pair of vacancies is produced, that is one positive ion site, that is called cation, and one negative ion site, that is here anion, due to the absence of the positive and the negative ions. So that is called actually the Schottky defect. So in a very general way, the definition will be when a pair of vacancies is produced when you don't find the equal number of positive and the negative ions. So such type of absentia of the pair of positive and the negative ion sides will call such thing such defect as Schottky defect. So here in the ionic crystal, when talk about the ionic crystal, there are two types of possible vacancies, that is cation, positive ion, and the anion, that is negative ion. So I think that you had a very clear idea regarding what is actually the meaning of Schottky defect, right? So when a positive ion from the interior of the lattice moves to the very, see, in depth, if you go little in depth of the Schottky defect, explanation of the Schottky defect. So, so what is actually happening, right? We just see with this particular aspect here. So when a positive ion from the interior of the lattice moves out of the crystal, so how it is moving? Exactly, it is not moving out of the crystal. From inside the crystal, the positive ion moving towards the surface. And these positive vacancies formed it's at its sides. And the formation of this positive ion vacancy result in excess negative charge inside the crystal. Definitely. See, if you remove that positive ion, it is moving from the inside the crystal to the surface. So what will be remaining there? More number of negative charge. And the to in order to maintain that charge neutrality, So a negative ion moves to the crystal surface, creating a negative ion vacancy at its site. So see, definitely whenever there is an increase in one of the charge ions, that is either it may be positive or negative, that we have to maintain the charge neutrality. So that is the reason that so the charge, in order to maintain the charge neutrality, so negative ion moves to the crystal structure surface, that is creating the negative ion vacancy at its site. Now this is the case in-depth understanding about how this vacancy shortcut effect has been created, which come under the category of point defect. Right. Now, what is the example? So just now, ionic, I said ionic crystal. We can just see that NaCl and CSCl, the cesium chloride and sodium chloride is an example of, and etc. You find a numerous number of ionic crystals here we talk about. So just take an example of NaCl and cesium chloride and sodium chloride and cesium chloride, which exhibit the Schottky defect. And in order to represent this in a very schematic manner, you can just see this particular figure here. So where you'll find that how this vacancies has been illustrated. Now, what is actually the meaning of, now I think that we had a very, what you can say, comfortable discussion regarding the Schottky defect. So in the later section, what is the second important aspect? That is the vacancy Frenkel defect, right? There's a very special case of vacancy and interstitial defect. So when I see we, sir, we haven't discussed about the interstitial defect. So interstitial defect is nothing but the whenever what is happening here is that the atom will automatically absorb inside the crystal. See, if there is a regular arrangement of the atom, and one of the atom of that regular arrangement will be absorbed by the crystal structure, uh, so that particular defect is known as interstitial defect. And definitely, in the later session, we'll understand it more clearly what is actually the meaning of interstitial defect. So now, for now, we just say that if you combine the vacancy and interstitial defect in the ionic crystal. So whatever the phenomena of defect is said to be a Frenkel defect. So when a pair of vacancies is produced at one positive ion site and one negative ion site, by replacing the positive and the negative ions, then this type of defect is called Frenkel defect. So simply you can say that a pair of vacancies is produced. See, a pair of vacancies are produced at the one of the positive and the negative ion side, and this can be replaced by the again the positive and the negative ions. Simply we can say that Frenkel defect is nothing but it is actually the sum of vacancy and interstitial defect. Again, see, if you don't understand it very clearly, then we'll go to the next slide. That it will be very useful for you. So to understand the Frenkel defect. So let us consider the uh, sequential distribution of the two charged ions, right? Oppositely charged ions. I'm talking about oppositely. See, if I say ionic crystal, definitely I'm talking about the positive and the negative ions. That is called the equal and opposite charged ions. So when a positive ion leaving the site and settles in the interstitial position, then it creates a vacancy in its position. Just now I told you. So you just take any of the charged ion. So let us consider if a positive ion is leaving from its regular site and it is settling interstitially, means it is actually absorbed by the crystals which are present, so atoms which are present inside the crystal. So whatever thing that has been remained there, so that is called a vacancy is produced, and thus the vacancy and the interstitial defects are created, and this pair of defect is known as Frenkel defect. And this Frenkel defect is just see a very clear and overall definition. It's a very general definition of Frenkel defect is vacancy plus interstitial defect is giving rise to Frenkel defect. So vacancy is the vacant atomic site. Interstitial, the atoms which are present inside the crystal, and one of the atom which is there at a regular position will leave that particular position and it will be absorbed inside the crystal, and we'll call such type of defect as the combination of vacancy and interstitial is nothing but Frenkel defect. So now again, definitely wherever you'll find any type of defect, charge neutrality should be maintained, right? So that is what we do, and the example is silver bromide, silver chloride, and zinc sulfide, etc., which exhibit actually the Frenkel defect. So the formation of the Frenkel defect is described in the following, what you can say, uh, this figure, a schematic figure you can just see here. Now here and here, right? So here your what you'll observe here. So vacancy and the interstitial in this atom is interstitial, and this is complete vacancy, and the combination of the interstitial and the vacancy is giving rise to a Frenkel defect. And here Schottky and Frenkel defect, we are talking about the ionic crystal. When I say ionic crystal, definitely you'll have a cation and ion, so positive ion and the negative ion. That is the reason that you'll find negative positive, and so on, the sequential order. So I think that you had I think a brief understanding regarding the Frenkel defect, right? So what is actually, see, I just now in the two slides, before the two slides, I told you about the interstitial defect. So the combination of the interstitial and the vacancy defect is known as Frenkel defect. Here we are going to understand what is actually interstitial defect. So what is interstitial? An impurity atom tries to settle interstitially, internally. It is settling down, and which is observed by the other atoms which are there, right, in the periodic manner. So so that particular definition, I just now whatever I told you, that is a very simple definition of interstitial. Now when you go for the a perfect definition, right? So that is when an impurity atom tries to settle in the interstitial space between the parent atoms of the crystal without displacing them. Such defect is known as interstitial. So interstitial impurities are much very smaller than the atoms in the what you can say the bulk state. The formation of the interstitial impurity defect is shown in the figure you can see here. The interstitial very small. So see, if some atom is leaving from its regular side, so it will be absorbed by the empty space. So and these empty space, from this empty space, this will be absorbed by the atoms, and such a defect is known as interstitial defect. So you can have a very good example of carbon atom. So if you take an iron, right? So carbon atoms are interstitial impurity atoms that are added to iron to make steel. You can just very simple example that we'll add some carbon atoms, and these carbon atoms, how you'll add to the iron? Interstitial impurity, as an interstitial impurity, and these interstitial impurities are added to form an steel, right? So now we need to go in detail of what is happening here. So just now you'll have a exam, should know that what type of example we can have for each defect. So what is substitution defect? So see, now till now we just got for vacancy. We started with the point defect. So point defect vacancy, and in that vacancy we had discussed about the Schottky and the Frenkel defect. And later in the section we just discuss now the interstitial defect. So under the topic of point defect, we need to understand the what is actually the substitutional defect. So when an impurity atom is impure atom. See, when I say a defect, definitely it will be an impurity, right? So generally, the thing which is coming into our mind is impurity. So when an impurity atom occupies the one of the positions of the parent atoms, right? So that is called, or you can say, when a foreign atom is, when a parent atom has been replaced with the foreign atom, so we'll call such arrangement as the substitutional defect. A parent, you see, normally atoms will be there in sequential order. If I remove that one of the atom which is already there, so that atom is known as parent atom, and instead of that, I am replacing it with the external atom there. So we'll call such a arrangement, such substitution as substitutional defect. So now, what you can say substitution defects are here. the formation of substitution, you can see these are blue is shown with a you can say a normal parent atoms, and here you'll find that a small orange part is here, so where we find that some impurity atom has been added to the regular parent atom. So example, zinc atoms are substitution impurities which are added to copper to make brass, right? Or else you can have the other example also. So that example is we can give for semiconductors. So these defects, electronic defects, are very special case of the point defects. So so what is actually the electronic defects? Electronic defects, they wherever you find that some charge distribution is not in an order in a solid, so that particular what you can say error or the defect is known as non-uniform distribution of charge in the solid is known as electronic defect. In a very simple way, we can just define non-uniform charge distribution in the solid is known as electronic defects. And these defects are produced when the composition of the ionic crystal does not correspond to the exact stoichiometry metric formula. So you need to see stoichiometric you already studied in your lower classes, but still you need to understand that what is actually the meaning of, in a general way, electronic device that is called the non-uniform charge distribution in the solids are known as the electronic defect, right? So now we need to understand it more clearly. So now see here we need, so just now we just completed our first part of the defect, that point defects. So we had just taken, we had a very, what you can say, brief explanation regarding the point defect, that is also zero dimensional defect. Under the point defect, you'll find the sub-classification as the vacancies, interstitial, substitution, and the electronic. So in the vacancies, we just discuss about the what is actually the meaning of vacancies and what is the interstitial defect and what is actually the, what you can say, the substitutional defect and what is actually the electronic defect. So now what is actually the line defects? Here we are going for the now zero dimension defect. Just now we have completed. Now we just go for the line defect. So here what is actually the meaning of line defect? So they are known as one dimensional defects also, and this is a linear defect, or we'll call the defect along the line is nothing but this. You'll find that the uh, lane along the line is nothing but the linear defect, and this is called one-dimensional defect. So dislocation is nothing but it is the one-dimensional defect around which some atoms are not aligned properly. So we'll call such a thing as the line defect. So now dislocation refers to linear disturbance of the atomic arrangement in a crystal. So dislocations are actually generated in a crystal due to the crystal growth accidents, so thermal stress, phase transformation, etc. So what is actually growth accidents, right? When the crystal grows in the, what you can say, lab, so definitely you'll have some insufficient what you can say uh, result. So definitely due to that insufficient or the prescribed result, pre-assume result, will get a will whatever the what you can say, the from the regular fashion will not get the expected result. So that is called growth accidents, right? So they can be observed in the crystalline materials with the help of electron microscope. You can just see this type of dislocation with the help of electron microscope. What is actually the happening inside the crystalline materials? So you'll find that dislocations that come under one dimension defect will be seen very clearly by using the electron what is microscope. So there are basically two types of dislocations, right? So edge dislocation and the screw dislocation. So when I say edge dislocation or the screw dislocation, so what is actually the meaning of edge and the screw dislocation? We'll just have a very clear idea. So most of the dislocation found in the crystal is neither pure edge or nor a pure screw dislocation, but contains the component of both these types, and they're called mixed dislocation. So here you'll find that the edge and the screw dislocations formations are not pure. So sometimes the screw dislocation and the edge dislocations are combined, and they will be termed as the mixed dislocation, right? So here we understand what is the meaning of edge dislocation. So in a perfect crystal, the atoms are arranged both in the vertical and the, you can see this is the vertical plane. We'll call when you talk about two dimension vertical plane, and this is your horizontal plane. So in the both vertical and the horizontal planes, as shown in the figure, from the figure it is very clear that the atoms are in perfect equilibrium, right? They are in a perfect equilibrium in their positions, and the lengths, bond lengths are at the equilibrium state. You can just see generally, if you have not understood this sentence, you can just say in a perfect crystal. We talk about perfect crystal, and the atoms are arranged both vertical and the horizontal planes, right? So here you find that again, what is actually the meaning of here? We talk about the edge dislocation, how this edge dislocation has been produced, right, in the atoms. You can just see here, if one of these, see this vertical, right? We talk about this vertical plane does not extend to the full length of, right? It is, see, actually this length, full length is 1, 2, 3, 4, 5. You'll find this is one vertical plane. So how many atoms are there? 5. Here, if one of the vertical plane is not exactly following the other vertical arrangement of the atoms, so we call, as you see here, you can just call this as, see, if one of the vertical plane does not extend to the full length but ends in between within the crystal, so we'll call such a dislocation as edge dislocation. And because of this dislocation, there will be a discontinuity. Definitely, you'll have a discontinuity, and the atoms are squeezed, and they are will be in a state of compression. And discontinuity, there will be a type of tension. So edge dislocation are represented a line imperfection, and we'll call such a dislocation as edge dislocation. And the representation of that edge dislocations in a symbol manner, you'll find that this type of, if you find this type of is nothing but, for example, if you talk about any, right, any in the mathematics, if you talk about any variables, I just take x-axis, y-axis for all, right, for all. So you'll have some symbol here. Also you'll have a symbol for the edge dislocation. This symbol indicates they are the representation of the edge dislocation. So here again, we will have a very clear idea regarding the edge dislocation. See here, when the incomplete plane start from the top, yeah, incomplete plane starting from the top, then it's called positive edge dislocation, and it can be represented by, you can see the schematic diagram. If the, what I say that, see, if when the incomplete plane starts from the top, you can see the starting from the top, then it is called positive edge dislocation, and it can be represented like this. And when the incomplete plane starts from the bottom, here see, you can just see, right here, the starting from bottom is here, starting from the top, here starting from the bottom, it, as it is, see, the slide which I'm trying to share you, so you can just write the same thing in the examination also without varying any sentence, right? So directly you can write in the same thing, you can write in the examination, right? Okay, just a minute. So now what we'll do here is that, okay. Now, what is actually the screw dislocation? Just now we just had a very clear idea about the edge dislocation. So, screw dislocation is also known as Berger's dislocation. So, here Berger is the name of the scientist, right, who has given us the information regarding the dislocations in the solid. This dislocation arises due to the displacement of the ions in one part of the crystal when compared with the other part, and this part comparison is nothing but you can show here. See, let us consider a perfect crystal having a regular periodic arrangement of the atoms when one of the phase, you can see, if one of the phase of the crystal is exactly cutting at the midway along AB, you can see it is exactly cutting at the along AB. You can see this figure, right? The AB, midway AB, and applying a shear stress parallel to the cutting plane. Now, this is the cutting plane. You can see this is the cutting plane. So, exactly, we are allowing very parallel to the cutting plane. A stress is applied to the crystal. So, here you'll find that is nothing but you can call that as edge dislocation. From the figure, one can see that the shift has been occurred at the length of one atomic spacing, which is dominating the part of the crystal and reached the line OO dash. You can just see. Uh, so this O dash will give us the exact assumption, exact semantic value of the screw dislocation. Along the boundary, the atoms are displaced and the two regions will be mismatched condition, and thus the dislocation of atoms takes place around the edge AB, which is known as dislocation line. And this dislocation, we say that it is a screw. You see why we are telling it is a screw dislocation? From the top surface, the dislocation of the atom will be in the form of a screw. When you see from the top, it appears that the dislocation of the atom is in the form of screw. So therefore, it is known as screw dislocation. So what is actually Burgess vector says? So the see whatever the assumptions we made, right, where the scientist has been made, that has to be proved mathematically. So we just now discussed about the edge dislocation and the screw dislocation. So we need to verify it mathematically, and so therefore the magnitude and direction of the lattice distortion associated with the dislocation is called the Burgess vector. You can now a very clear idea what is actually the meaning of Burgess vector. So it is the magnitude and direction of the lattice distortion associated with the dislocation, and it is called Burgess vector. And these dislocations are quantitatively described by Burgess vector, which is known as which is represented as small b. So this dislocation, right, the geometrical way has been represented with b. The magnitude of the Burgess vector is found by drawing. So how you can find out the ICSE? In the first sentence, we said that magnitude and direction of the lattice distortion. So how you will show it? So by means of some closed circuit, will show that there is a dislocation line, and we'll call such circuit as Burgess circuit. Why it is called circuit? I'm let you know definitely in the next. So you can just see. Now again consider a perfect crystal. Now in the figure you can just see the point P. Where is the point P here? Here. So we go from here. I'm going up to P. So how many steps I require? 1, 2, 3, 4, 5, right? And down by 6 steps. Yeah, this is right. 1, 2, 3, 4, 5, and 6. And finally, move towards the left. 1, 2, 3, 4, 5. Right. So and move to the left to do also. And 5 steps to reach the point P, and the Burgess circuit is closed. Here, see again, I'm repeating. Starting from the point P, we go up. See, starting to the point P, I'm going up. So how many? Six steps, right? From P, I'm going to the sixth steps. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 5 steps, right? And move down by 6 steps. 1, 2, 3, 4, 5, 6. And finally moves to the left. 1, 2, 3, 4, 5. So now the point P and the Burgess. This is called Burgess circuit, right? So now consider the case of edge dislocation. I said we just taken edge dislocation. This is the top dislocation. I say this one. So when the same operation is performed on the crystal, we end up to the point Q, right? Instead of the starting point P, how we have to move an extra step to return to the point P. So now this is the extra step that has been done to move to the point P. Our aim is to move to the point P. So now, how I will move the point to the point P? So point P, the magnitude of this direction of the step, magnitude and direction of the step is known as Burgess vector, which has been shown by the vector, right? QB bar is equal to B. So the Burgess vector is perpendicular to the edge location and parallel to the screw dislocation. Now consider the Berger circuit in the crystalline which had the screw dislocation in the perfect crystal starting from the again point P. You can see if you talk about the Berger circuit. So if you trace a Berger circuit, so that is P N O P, that is called shown in the figure. So in the case of a screw dislocation, right? So the circuit will not be completed. You can see this is screw. It is in the shape of screw, right? You can see here, not completely. So the what is that dislocation FA? You can see this FA is magnitudely given by the Burgess vector. B is equal to parallel to the, so Burgess vector is parallel to the screw dislocation, right? So now, so we need to here I'm just stopping it at the line 1. So here I'm just what you can say. Uh, uh, we just go for our what you can say video. We'll show the video right before moving forward. So in today's discussion, we had a very clear idea about the point and the what you can say line defect, 0 dimension and 1 dimension defect. So now I will show you a video that will understand what is the engineering material is all about, right? So now we'll show you that video. Okay. Just a minute, I will show it for a while. I'm searching it. I'm searching the video. Right, I will show you the video of the today's session. Yeah, just a minute. Yeah, now see, now we'll just have a, we'll see the video of engineering material.
Materials. Materials are all around us. We use them in our everyday life. But what are the most common materials? What do they make? And what properties do they hold? These are the key insights that we will try to uncover in this module. For engineering purposes, materials can be divided into 4 key areas. The first is metals. Metals are the widest used of the 4 materials. Even if a material is not made of metal, metal will have been used at some point during its manufacture. Metals are used for everyday objects like cars, buildings, and bridges, but also go into extreme applications like jet engines, mining equipment, and space exploration. Even the tallest buildings in the world are only possible due to metals. The second material is polymers, which includes plastics. Polymers are widely used in many different industries. Natural polymers consist of amber, wool, silk, natural rubber, and cellulose, which is the main constituent of wood and paper. These natural polymers have been used for centuries. More recently, synthetic polymers have been produced, and these have revolutionized modern society. These include synthetic rubber, nylon, PVC, polystyrene, silicon, and many more. The third is ceramics. Ceramics have been used for thousands of years, and the most common two are glass and clay. Clay was the first material that we learned to transform into another state using fire. This was done about 29,000 years ago, when clay was formed into decorative figures. Much later, clay was used to form items like jugs and bowls. Glass, which is mainly made from sand, was mastered by the Romans, who unlocked the secret of blown glass by mixing it with minerals. The Romans were the first people to use glass for windows. The fourth material is composites. A composite is a combination of 2 or more materials. Composites have been used for centuries in the form of concrete. Again, it was the Romans who really mastered the process. In text from 25 BC, Different aggregates are discussed for use in lime mortars. In 1853, steel bars were first added to concrete, making it one of the widest used composites, reinforced concrete. Metals can be divided into two subgroups, ferrous and non-ferrous. In ferrous metals, the main constituent is iron, and this group consists of steels and cast irons. For the amount of strength that is achievable in steel and cast irons, it is a cheap material. This is because iron is one of the most plentiful elements in the Earth's crust. Non-ferrous metals include any other metals. Some examples are aluminium, copper, zinc, titanium, and nickel. Metals have good electrical and thermal conductive properties. They are ductile, strong, tough, and have strength at temperature. Polymers are organic carbon-containing molecular chains. They have a wonderful array of properties and are primarily made up from hydrocarbons. These are the building blocks of plastic. Hydrocarbons are a byproduct from petroleum industry, and due to this, they are abundant and therefore a cheap material. The carbon and hydrogen which make up the plastics are the key to how they work, because they can form together to produce long chains. This enables plastics to be versatile and easily processed. How the material is processed can produce the desired combination of properties. The strength can be varied, the toughness can be varied, they can be a good conductor of electricity and are often very good insulators. Again, ceramics can have a wide array of properties, and in recent years we have really begun to understand them. Semiconductors have been produced which, when cooled, have virtually 100% efficiency in electrical conductivity. To put this into perspective, current electricity cables lose about 5% of electricity through resistance. With the loss in the world's electrical energy for 1 year, you would be able to power over 3 million washing machines constantly for 100 years, meaning that each person on the earth could run a washing machine constantly for 15 days for free. Ceramics are an inorganic, non-metallic material. They are chemically bonded and can have a structure that is crystalline, non-crystalline, or a mixture of both. Ceramics are known for their lightweight, high strength, high hardness, good heat and wear resistance, making them excellent for furnace linings, although ceramics can be brittle. Composites consist of a matrix or binder and a reinforcement. Composites affect our everyday life, probably without our awareness. Concrete is likely to be the most common composite and has shaped the modern world we live in. Concrete consists of a cement matrix and a stone or aggregate reinforcement. Another is fiberglass, with a matrix of plastic and a reinforcement of fine strands of glass. In the 1960s, scientists set out to make plastics as strong as metals. Through their research, they produced carbon fiber. This is also known as carbon fiber composite, and it is made from fibers of carbon and plastic, similar to glass fiber. This gives unique properties of strength, stiffness while being lightweight, but carbon fiber is very expensive. Only over the past 60 years have we really understood metals on an atomic scale. In metals, atoms are arranged in an orderly manner, giving them a crystalline structure. Metals consist of two common arrangements of atoms, one with an atom at each corner of a cube and one atom at the center. This is called body-centered cubic. The other has an atom at each corner of a cube and one atom on each face of the cube. This is called face-centered cubic. Mild steel arranged in a crystalline manner should have a strength of approximately 20,000 megapascals, which is equivalent to supporting the weight of an elephant on a 1 mm thick piece of wire. But mild steel has a strength much lower than this. It has a strength of approximately 1,000 megapascals, or a strength 20 times lower, which is equivalent to supporting the weight of a sheep from a 1 mm thick piece of wire. The reason that steel is reduced in strength is due to the imperfections in the atomic structure. These are called dislocations. Normally, when we think of crystals, we imagine that we can smash them under a load, like a hammer. But the interesting thing about metals is that when pressure is applied, the atoms can move, and this is how they can be formed and worked into different shapes. The dislocations help this deformation process. In metal, the atoms are arranged in groups. These groups are called grains. These are evident when you look at a zinc-coated surface, or what is known in the industry as a galvanized surface. These grains can work both in favor and against the steel. They can increase the ductility of the steel, but where the grains join, the grain boundaries, are areas where impurities collect. Metals can be strengthened by adding more than one metal together, such as copper and tin, to make bronze. In this example, the two combined has far greater strength than each of the individual metals. The sum is greater than the parts. We can also change the properties of metals by adding non-metallic elements, like carbon. If we take steel, there are hundreds of steels, all with slightly different properties, some tough, some strong, other resistant to rust. These steels are produced by the same principle as bronze. We take one element, iron, which is the bulk of all steels, and add another chemical element, often called alloying elements, to it. To name a few we could add: carbon, manganese, nickel, copper, molybdenum, boron, chromium, niobium, titanium, and vanadium. In this way, we can tailor a steel to a specific application. So, we take our grains of iron atoms and our alloying additions, which often have a different atomic size. For example, carbon is small, nickel is slightly smaller than iron, and molybdenum is slightly larger than iron, and add them together and we get a distorted structure. When we add atoms that distort the atomic structure, this makes it more difficult for the atoms to move around and makes the material stronger. Depending on the type and amount, we can make a metal much stronger. The smallest elements, like carbon, lay in between the iron atoms. These are called interstitial. We have the largest atoms which replace an iron atom, like molybdenum. This is called substitutional. This type expands the structure. Or we can have smaller substitutional atoms, like nickel, that collapse the structure. So, in summary, engineer materials can be divided into 4 key areas: metals, polymers, ceramics, and composites. Composites are as high-tech as carbon fiber and as abundant as concrete. Composites are a combination of 2 or more materials. Composites consist of a binder and a reinforcement. Ceramics were the first material that we learned to transform from one state to another. Ceramics are inorganic, non-metallic materials. We have really begun to understand ceramics in recent years with semiconductors. Polymers have revolutionized modern society. Plastics are made from hydrocarbons, which are a byproduct of the petroleum industry. This makes them abundant and cheap. How the polymer is processed has a large influence over its properties. Metals are the widest used of the 4 materials. Metals are divided into 2 subgroups: ferrous, containing iron, and non-ferrous, not containing iron. Iron is one of the most plentiful elements in the Earth's crust. This is used to make steel and cast iron, which makes them efficient in terms of cost per the amount of strength achievable. The atoms in metals are arranged in an orderly manner. They have a crystalline structure. The theoretical strength of metals is much higher than reality due to dislocations. The crystals of metals are arranged in grains. The properties of metals can be manipulated by adding other chemical elements to them. These elements distort the atomic structure, making it more difficult for atoms to move around.
Now we just I take a leave for this class, right? So we'll again meet in the next class. Thank you everyone for your patience.